Okay, so my name's Daniel. I'm going to talk about heterogeneous graph neural networks. I'm going to take as sort of our use case and our motivation, something that we're working on, which is track reconstruction for high luminosity LHC-like data sets. So I'm working on this with not only the Exotrex group, but also the group at L2IT, in particular Sylvain and I are trying to nut it out. So what is a heterogeneous graph? So I was inspired by Andy's graph of the CTD participants. So we could imagine structuring a CTD friendship graph, and this is something that you would actually do if you worked at Facebook or whatever. And we can do it in a kind of intuitive way. We can set up a set of properties, features for each node, which is to say each person. And we could basically one hot encode a bunch of likes. And I think, back in the day, this would have been what you actually did, say in MySpace or something, where the number of things you can like is finite. It makes sense to encode these in this way. And then we want to predict, for example, given Andy and Paolo's likes, we want to predict what Marcus likes. So you could do this, but at some point you want to go beyond one hot encoding and padding and so on, and you want to be able to encode the concept of a like into some space. So we can imagine encoding the kinds of foods you would like, the kind of alcohol you would like, the kind of entertainment you would like into a space and attach it to the nodes. And it begs the question, how do you do your regular graph neural network? I mean, at the end of the day, it ends up looking something like incorporating that information as a node in itself. And so in this case, now we have participant or friend nodes, people nodes, but we also have other concepts as nodes that don't really fit into the same node type. So we have an alcohol node, an entertainment node, a food node. And then of course, that means that the actual relationships are different, right? A person-to-person node is a friendship edge, whereas a person-to-concept or like node is the concept that they actually are interested in that node. So then we can go away and try and attach concepts to each edge. And by learning relationships about those edges, we can try and also make edge predictions on other people's nodes. So we might predict that Marcus is interested in heavy metal songs based on the friendship graph and in his neighborhood. That's the idea of heterogeneity. There's a lot of ways of implementing this. So this is from the PyTorch geometric documentation for heterogeneous graphs. It's a little bit more dry than the other example, but still it's useful in this kind of benchmark problem of predicting who wrote what paper or what field someone is interested in, to embed fields of study, papers that they've written, authors as different nodes, and they have different relationships with each other. So as I said, you can do this with padding, very, very long one hot encodings and so on, and drink up. But you can also, and so in this way, you would use a homogeneous GNN. And as such, it's been traditionally a bit hard to compare the performance of heterogeneous GNNs with homogeneous GNNs because there's more than one way to skin a cat. But this paper by Zhang et al. Did this. I mean, they did a very rigorous comparison of encoding heterogeneous information as long vectors and using homogeneous GNNs. And they showed that there were a lot of mythology in the literature that needed to be fixed, but basically they standardized a lot of these things and built a standard heterogeneous model that did indeed outperform embedded homogeneous models, if I can put it like that. So there is a proof of concept here that heterogeneous GNNs, which is to say treating different nodes differently and having different MLPs for different nodes and edges, is indeed the right way to treat a heterogeneous graph. And the community reflects that. There are now heterogeneous versions of most of the most popular GNN libraries. So PyTorch Geometric has now native support for heterogeneous GNNs. DGL has heterograph structures. There's even a new library, GNN Keras. I'm not sure if it's going to take it off, but I noticed it a few days ago, and it out of the box supports heterogeneous GNNs sort of from day one. So that's a nice sign. Of course, we don't need to use a library, and I'm not going to use a library here. That is, it's nice, I think, in general, to do all this stuff by hand the first time. And I'll show a way of doing that I think is quite intuitive. First, I want to motivate why at least we are interested in heterogeneity. We have this pipeline that's been shown a couple of times, so I won't spend too much time on it, but basically, one of the final steps is, given a constructed graph, we want to be able to classify edges as either belonging to the same track or not. And this is our current performance, which was also shown in Charlene's talk. And you can see that the performance takes a dip at low eta, so in the barrel region. This is frustrating, and we think we can fix it. So what's special about the barrel strip region is that in this region, space points are constructed from a pair of clusters, rather than in the pixel, where they're constructed from a single cluster. So that means there's something conceptually different about the space points in pixels and in strips. And you can see, in fact, that here's an example at the top of an actual space point being reconstructed in red. You can see that space point is quite far from where we would expect it to be. That's no one's fault. That's just how the hardware is built, and that's the information that we're given. But it begs the question, is there a way to include the underlying information about the clusters in the space point node itself? And naively, it's not straightforward, because, of course, up until now, we've had all the nodes having the same structure, which means they each have a space point, X, Y, Z, and pixels only have one cluster. How do you treat these nodes differently? Well, of course, the answer is heterogeneous graphs. We've already had a couple slides on how GNNs work, so I will only show this to differentiate how heterogeneous GNNs work. So at their heart, we have a message passing function, which encodes information on each node and passes it along each edge and aggregates it in a neighborhood. To extend this to the heterogeneous case, we could imagine edges in our graph. Some of those nodes come from pixels, some of them come from strips. So let's imagine trying to predict whether a pixel to pixel edge is true or not. Or we simply take our two sets of space points and we encode them along the edge. But of course, when we're going from pixel to strip, we now have one set of cluster features on our pixel node and two sets of cluster features on our strip node. So even just dimensionally, we can't use the same MLP as we did for pixel-pixel. So this is kind of blocking. So we need a different MLP, just intuitively. And we found that just applying this out of the box already gave us significantly better purity in the graph construction stage. So that was sort of our motivating example to think about putting this heterogeneous structure into the GNN itself. Of course. So how does this work? Well, we take our pixel space points and our strip space points, and we basically give a different MLP to each combination of edges. So we have a pixel-pixel edge, a strip-strip edge, and a pixel-strip edge. But of course, that's assuming we only have two types of nodes, a pixel node and a strip node. There's no reason to stop there. We could have a different node type for every region of the detector. Because in some sense, these are different hardwares. They're conceptually different and they perform differently. So there is a physical motivation to treating each section of the detector with a different node type and therefore a different edge combination type. So in the case where we might have four, is this a pointer? Right. Four node types, which is to say pixel barrel, strip barrel, pixel end cap, strip end cap. Then of course we need four choose two combinations of edge. We need a 0, 0, a 0, 1, a 0, 2, and so on. So of course the trade-off here is that now we have 10 edge models, and 10 models is larger than one model, takes longer to train. We need more statistics to train it properly. So it's not, you're not getting a free lunch. I mean, there is a cost to incorporating heterogeneous information. And I'll just mention that you could, of course, have heterogeneous models with the same node features. And indeed we do. We have pixel node features in the barrel and the end cap. They're both three-dimensional pieces of information, but still there's maybe some motivation to treating them differently. And I'll just emphasize that, yes, based on the number of nodes you have, the number of edges you have, you need a different MLP for each type. So that's the basic idea. You don't have to stop at just encoding your nodes and edges. You can have your N encoders and N choose two edges, and then pass these through your regular message passing node and edge updates. Of course, you could have these node networks and edge networks themselves be heterogeneous. So you encode your nodes and edges based on the region, and then you also pass the messages based on the region. And then, of course, you could do the whole thing. So we're trying to think of this in terms of different levels so we can abstract out and sort of do hyperparameter scans in a sense. So you could have a homogeneous GNN, which is a sort of level 0. Everything is treated as the same kind of edge and node. We can have heterogeneous encoders, level 1. We can have heterogeneous message passing, level 2. And even our output could be heterogeneous, which is sort of the kind of natural limit of how heterogeneous you can make in this paradigm. So pretty quick, I'm just going to skip right to the end, I guess. So these are the results we have. We have two models that we threw at some toy data. We knew that this data was not performing very well on the barrel strip. This is high pile-up data and TT bar. We have a homogeneous GNN, and we have our heterogeneous GNN. We basically scanned over all these different possibilities and different combinations of regions, because it's not obvious which choice is the correct one. So we picked the best performing one, which happens to be actually only heterogeneous encoders, but treating your node and edge updates homogeneously. And a 3-region heterogeneity. So your pixel, all your pixel nodes are treated the same. Your barrel strip has a dedicated MLP, and your end cap strip has a dedicated MLP. And we can see on some arbitrary scale that the heterogeneous performance, much better recovers the efficiency and purity that we lost initially in that barrel region, as we hoped and as we expected. There is this odd drop in performance around the center of the detector. This is appearing in all the heterogeneous models. So this is a quirk that we need to investigate.
Can that be a biasing effect that now you're picking up more edges on the outer side? Yeah, that's apparently what it says. Green more outer, you pick that up, you effectively change your denominator of the track selection, I think.
Right. I mean, yeah, you could fix this with some sort of weighting that depends on the region. And this is a big deal. I mean, we need to balance these regions more carefully now, because at the moment, all of our learning rates the same, our loss function is the same, the weighting's the same. That's clearly not the most rigorous way to do it, I agree. And it may well just be that we need to treat the loss function for this area differently to this area.
Yeah.
Are
those different? Those are different regions, right?
Yeah.
In your
yeah.
So you're losing the sort of in the central balance, but you're getting.
So if you remember, the score function we've coded for the track ML, that was handcrafted to basically enforce track completeness, so giving more weight for the last and the first hit, in order to say that we want to have complete, but it was not physics like check, but hardly led to a good result. So if you treat them equally, yeah, what you do here if you have no weighting, I can imagine that I have another idea.
No, I think that's a good way to think of it. And moreover, we should, regardless of the heterogeneous piece of this puzzle, we should be weighting these tracks not just by whether they're true or not, or background, but PT, length of track. I mean, we should be teaching the model to prioritize interesting tracks, right? Yeah. And especially when it's heterogeneous, because then we're plagued by like low statistics in certain parts of this region, so it's not learning as quickly and so on. This was a toy. We need to reproduce this over the entire ITK data set up to basically what we have currently that Charlene showed a couple of days ago, and understand how does this improve track reconstruction, or how does it maybe deteriorate it in some areas, and how do we fix that? Can we include more than just, you know, the three-dimensional cluster positions? Can we include charge deposit information and so on? Yeah, can we balance these? I think that's going to be a key piece. And at the moment, we're using interaction network. Maybe that's not the best network for heterogeneous GNN. That's not clear to me. So yeah, I'll leave it there. They are, I mean, quite straightforward to implement. I encourage you to have a go just doing it by hand. But there are libraries that will do it for you nowadays, which is nice. And they are physically motivated. I think they're the best way to treat pieces of information that have different conceptual type. And if you have a use case that fits this, I mean, speak up and yeah, we should talk about it. Thanks.
I have a question regarding.
Go ahead.
I'm sorry, actually. So for this different pieces of detector, you have the end cap, you have barrel. Are they all silicon detectors give you the same features for the heats, or they give you different, like a charge or energy or some different features? That's the reason why you use heterogeneous node type.
Even if they were all, well, the main motivation is that they're constructed differently. Where's the picture? So this is So this is how a strip. Well, you can't see the pointer. This is how a strip space point is constructed. It's the red dot in the graphs and the plots on the upper right side. On the other hand, a cluster space point is simply mapped directly to a cluster. Sorry, a pixel cluster is mapped directly to a pixel space point. So the way that they're constructed, so the underlying construction of these is different. They have different input information that you could leverage, even if the feature sets of the clusters were exactly the same. I mean, they're not, they have different meanings, right? But even if they were the same, one space point in the strip equals two clusters. So
Oh, I see.
It's conceptually different, right?
Thank you.
Daniel, we actually do have another type of node, if you think about it. Yeah. because that what you show is active hits, kind of towards a bit along the way where the discussion we had at the Institute Pascal on the Pascalos in GANs, that the way we build our simulation is we basically model only extract the information from the active part. Now at the end we have information about nodes, which is passive material in the in between here, wherever it is, that where we have information, we have no measured information, but we have a regulator, which is the amount of material which is passed. And that gives different effects for different particles. So I wonder whether one could encode something like scattering and energy loss nodes into this graph at certain levels, because that could give you a handle on electron reconstruction. That's interesting.
Yeah, no,
that is information, but naively via the message passing. And if you think about your graph before, where you had you lost suddenly age classification in the pixels compared to the strips.
Yeah.
Now think about the fact there's a material layer between pixels and strips, right? If this is not captured well enough by your model, because there's no information that flows into it, and then you suddenly pick up the segments in one part, it might just have an effect that the inner segments are not compatible anymore, because you haven't modeled that in between there's some sort of information flow that has to do with the material. It will complicate it a lot, but voila.
Yeah, I mean, well, it's always a trade-off, though, right?
We're hiding in the graph network approach. You're hiding the fact that there is material. No, you're not ignoring it. Is material between the hits in. You rely on the fact that the edge relations can basically have enough freedom to adapt to the material that is in between those.
Right. Yeah, in some sense, a strip pixel edge should capture the latent space in some way that represents the material between them, right? And of course, it would be easy to learn it if we teach.
The question is, does it? Yeah. And since we know how much material is everywhere there, you can actually have a node in that regulates.
No, that's interesting. Yeah.
I'm not coding this up though.
No, but yeah. No, I mean, it's not obvious and straightforward, but it should be possible. Nice, yeah.
Yeah, and since you are treating the strips no separately, I mean, did you think about, because most of the complication you're having is pure geometry. Huh? You could either tell when you do the message passing, do the zeros order corrections explicitly and correct the space points, as we do in classical software, or you do like what was done for the flavor tagging in Atlas. You make it a secondary goal for the training. That you let the GNN predicts the correction and you put in the explicit one as to maybe get a better handle on this relatively simple geometry.
Yeah, no, that's a nice. I mean, build in some sense the next what a CKF or something might do, where it's trying to resolve.
Yeah, I mean, it's basically the way you in a projective world are looking onto which depends on. I mean, this is why in the barrel is particularly difficult, because you have tracks coming from this direction and this direction, and if you have a small angle stereo, the space point positions change quite a lot, right? I mean, and those things, now that you have separated this, you could probably encode in the system and regain more control on the space points.
Yeah. We sort of allow this in the I mean, we have this built into our classical algorithms by the on-track calibration that you say, once I'm on, in this case, on a branch of the graph, yeah, you can with a bias, but hopefully with a minimal bias, use this information to re-evaluate the cluster, or in this case, space point position.
But Andy is saying, he's telling you where the function is, which you can use.
Yeah, okay.
Because it exists as a function in ACTS. You can just simply.
Yeah, but here you can learn it. Yeah, you can learn the correction probably.
Right, I guess the toy would be just to add in this fitter function into the loss somehow, optimize it, but then also the next step, I guess, would be treat it as an MLP, build it into the message passing. Yeah, that's a really good idea.
I mean, it might actually be better to have it as an auxiliary training goal.
Yeah. Did you? Yeah.
Yeah. This is like sort of a comment, but you may have like a response to it. You showed a chart comparing the different types of like ways you could impose the heterogeneity on the architecture.
Like this?
No, where you started out with just the fully homogeneous approach, and then you considered like heterogeneous architectures.
Yeah.
Encoders and yeah. Like that got me thinking that there's this kind of other, or actually most of the time when you see heterogeneous architectures referenced in the literature, it's more that you've got a node representation that's common to a lot of different node flavors, but you've more or less just zeroed out the node features that aren't relevant to this particular flavor of node. And that to me that's like somewhat different than a fully heterogeneous architecture like this, where you've actually got separate MLPs. I was curious if you'd tried just the zeroed out features approach here and how it compared to a fully heterogeneous approach.
Yeah, I mean, yeah, we should run this with just padding it out. No, the answer is we haven't tried it yet, but we should, to prove that this is indeed outperforming the sort of naive heterogeneous, like pad of the heterogeneous, right? Yeah.
Right.
Yeah, I think you're right.
I mean, there is, I think, some, how do you say, crosstalks between two things, which I think are happening here. One is that we have different features that we could pad out or not, but also that we're kind of giving a hint to the network that, we have strips and pixels and they don't look like each other. Whatever numbers you put in your feature table, they really are different. So there may be some sort of, I think you could say crosstalk challenges, right? When you pass some information through the structure of the network.
From a computational aspect, if you change, like if you get heterogeneous node edge features, is there any how this destroys or this affects the computational performance, since you have practically you work with less, let's say, symmetry of the computational.
You mean in terms of really operations per second
or
whatever?
Yeah.
I mean, at the moment, the way I implement it by hand, it just scales by the number of networks or node types and edge types, which is really naive, right? I haven't looked deeply into it, but I'm sure these are smart guys.
These are
right. So I'm sure they're scattering and doing stuff in parallel, and you can. In theory,
I wonder how much you basically destroy the possibility to have a parallel code execution paths when suddenly the paths don't look the same anymore, because that's what effectively is going to happen, right?
Yeah, I mean, in a sense, it's like a combination of masking things out, and you could be able to mask these and do them simultaneously. I mean, PyTorch really does this well. I haven't exploited it, in a clever way, but I'm sure these libraries must. But yeah, I haven't seen a good plot of like scaling heterogeneity versus homogeneity yet.
For this heterogeneous network implementation, I think this is appropriate because from my understanding about the heterogeneous network, they're trying to collecting heterogeneous paths from the end to end. Then you're trying to get attention. But from your approach, actually, sort of you don't need that heterogeneous path to connect to hits. You only need the edge. So your implementation using similar to the attention network, different attention for different node type. So that's, I think this is appropriate. You probably will not get more performance gain by choosing the full scale heterogeneous network.
Could I ask actually if you've checked how this, like essentially the price you have to pay both in terms of training and inference times when you go to this heterogeneous model?
Yeah, I mean, I guess it's similar to what Andy was saying. I mean, at the moment it scales both in training and inference. So memory is flat. In fact, this is actually a little bit more memory efficient because you do the networks one at a time. So you're matching your edges. And with checkpointing, you can actually make this take less memory. The time for training, the time for inference scales linearly with the number of edge networks, really, because it's your edges are a combinatorial increase. 3 node types is 6 edges, 4 node types, 10 edges. And so you have 10 edge networks, and I just loop through them, really dumb, but probably you could make it scale much better than linearly with number of edge networks.
Although each one of the sub networks is probably 1/10 of the edges, right? Something like
Exactly.
that.
Yeah.
So you have 2 things which are fighting each other.
Right. Yeah. There's still some masking in a
Oh,
yeah,
for sure.
but yeah, I agree.
For sure.
It's not.
It's not like
It's not-
10 times. It's not like 10 times slower. Right?
No. In reality, it's, I think 10 edge networks, it's about 4 times slower to train as a order of magnitude, kind of rule of thumb. Yeah.
All right. We're gonna kick you out.
Thanks.
Thanks, Daniel.